imagine that I have a charge right here of Q. I'm going to create a Gaussian sphere around it, where Q is at the center. So this distance here is R. And I want to know, what is the electric flux coming out of the surface? Well, I know that the electric flux is E dot A if the electric field is constant, or if the electric field is not constant, E dot dA for the calculus-based group, for the non-calculus-based group. So if I take this point right here, I have an electric field coming out of it at that point, and I have an area vector in the exact same direction. Call it E1A1. Over here, I've got some electric field E2 and some area vector A2. But if the circle here, or sorry, sphere is equidistant from the center, which is basically the definition of a sphere, then my electric field magnitude is going to be the same. My area vector is going to be, well, the magnitude of my electric field is going to be the same. The magnitude of my area vector is going to be the same. At any point on the sphere, my area vector and my electric field are in the same direction, and so the dot product just becomes EA at any particular point. We're going to add them all up. In essence, what we end up with here is we end up with some small little area here plus some small area there. But you add up all the areas, you get the total surface area. So this ends up being E times the surface area of a sphere, which is 4 pi r squared. And that is equal to, well, the electric field. We know the electric field at some distance of point there. There's a formula for it. The formula is the electric field is equal to KQ over r squared, or in this case, capital Q. So K capital Q over r squared, in the radial vector, in the radial direction. Looking in the slightly more sophisticated form, K, this Coulomb's constant, is 1 over 4 pi epsilon sub naught Q over r squared, r hat. So my magnitude of my electric field here is going to be Q over 4 pi epsilon sub naught r squared over times 4 pi r squared. So that is my electric field magnitude, and that's the area vector. The 4 pi r squareds cancel out. What I'm left with is Q over epsilon sub naught. Now this Q is the charge that is inside. That is the enclosed charge. So we can generalize it that the electric field through any closed surface is equal to the enclosed charge over epsilon sub naught. This is Gauss's law of electricity. Now, I haven't done the full proof of it. The full proof is a little bit more sophisticated, and so, but since this is a pseudo derivation, I am taking this. I did it for a specific case, but this is true, regardless of the shape of the surface. And also, this is the first one that textbooks generally derive, which is later to be considered one of Maxwell's equations. Maxwell never claimed it as his. This is something that came after the fact.